Section 3.7 Optimization, Example 3. You have been asked to design a 1-liter oil can shaped like a right circular cylinder. What dimensions will use the least amount of material? So, a right circular cylinder is going to be a can. So here's a picture of what it's going to look like, where this will be the radius, and here's the height of that can. Now, since we are being asked to find the least amount of material, what we want to do is we want to minimize the surface area. So, if we are going to minimize the surface area, that means we need the equation for the surface area of a right circular cylinder. The surface area for a right circular cylinder is going to be 2 pi r squared. That covers the area of the top and the bottom of the cylinder. And then we're going to add in 2 pi rh, which is going to create the area of the sides. Now, this particular problem is going to be in terms of two independent variables, the radius and the height. So we will need a second equation to be able to substitute one of the variables out. Now, up in the problem, they told us that this can is supposed to hold a liter of oil, which means that it's going to be 1,000 cubic centimeters. So, the volume of a right circular cylinder is pi r squared h, and we know that it has to be 1,000 cubic centimeters. So what I can do is solve for h, which is going to be 1,000 divided by pi r squared, and then I can take that and I can substitute into my primary equation. Remember, the primary equation is the equation that we want to optimize, which in this case we want to find the minimum. So the area is going to be 2 pi r squared plus 2 pi r, and we're going to replace h with 1,000 over pi r squared. Now we can do a little bit of cleaning up, a little bit of reducing. So pi r, or 2 pi r squared plus the pi cancels, one of the radius values cancel. 2 times 1,000 is 2,000 divided by r. So before we take the derivative, let's pause for a minute and talk about what the feasible domain is. The r is talking about the radius of this can. So the r definitely cannot be negative. However, we don't have any restrictions on how wide it can get. So we can have a really, really tiny radius and a really tall can, or we could have a really short can with a wide radius. All we know is that the radius definitely has to be positive. Alright, so let's go ahead and take the derivative. So a prime equals 4 pi r. And for the derivative here, think of this as being 2,000 times r to the negative first. So negative 2,000 over r squared. In order to find the critical values, I personally find it easier if I have a single fraction instead of two terms. So I'm going to find a common denominator between these two, which means I'm going to multiply this first term by r squared over r squared. That gives me 4 pi r cubed minus 2,000 over r squared. So in order for us to find the critical values, we're going to be looking at when the top of the fraction is equal to 0 and when the bottom of the fraction is equal to 0. So the critical values are going to be when r is equal to, from the top one, when I set this equal to 0, we end up getting approximately 5.41926. So we want to test this to see if that truly is a minimum value. Now remember, we're not going to test anything less than 0, but we do not have any maximum. So I'm going to put that 5.41926 on our number line, test it in the first derivative. Now if I test a value between 0 and our critical value, like a 1, I end up getting a negative. If I test something larger, like a 6 or a 10, I end up getting a positive. Since my derivative changes from negative to positive, that means that the area is going to change from decreasing to increasing, which means this value right here will be a relative min, which is what we were looking for. Now, the direction said to find the dimensions that will use the least amount of material. So the dimensions that will use the least amount of material is going to happen when the radius is 5.41926 centimeters. And to find what the height is at that time, the easiest place would be back up here in our secondary equation. So if I take the radius of 5.41926 and I plug it into this equation, I get that the height is going to be 10.8385 centimeters. So we will use the least amount of material, however, still hold a volume of 1 liter with the dimensions right here.